Welcome to the Explainer. Today, we are taking a massive leap. We're transitioning from just, merely observing how things move to deeply understanding exactly why they do. We are going to unlock the fundamental laws of classical mechanics that govern literally everything around us, from a falling apple all the way to a rocket launching into space.
To guide our journey, here is our agenda. First, why do objects move? Second, first law, the inertia rule. Third, second law, force and mass. Fourth, third law, action meets reaction. And finally, number 5, dynamics in daily life.
Okay, section 1. Why do objects move? So when we study physics, we usually start with kinematics. Now, kinematics is great, but it's really the surface level. It answers the question of how an object moves by looking at speed and distance. But dynamics? Well, dynamics digs much, much deeper. It answers the ultimate question of why objects move in the first place, investigating the invisible forces that constantly dictate our physical reality.
Think of this as our ultimate why toolkit. Dynamics is the branch of mechanics that studies the relationship between external forces, like pushes and pulls, and the changes in an object's state of motion. If an object speeds up, slows down, or changes direction, dynamics helps us figure out exactly what invisible hand pushed or pulled it.
Moving right along to section 2, first law, the inertia rule.
Sir Isaac Newton dropped this absolute gem back in the 17th century, and it brilliantly illustrates that objects are, fundamentally speaking, incredibly lazy. I mean, they just want to keep doing exactly what they're already doing. If an object is resting, it absolutely refuses to move. If it's already moving, it refuses to stop, unless, of course, an external force makes it. Picture a book sitting quietly on a table. Its velocity is 0. Its acceleration is 0. It stays that way. Now imagine a hockey puck gliding endlessly across a perfectly smooth, completely frictionless sheet of ice. Its velocity is constant, and its acceleration is 0. In both cases, the forces acting on the objects are perfectly balanced. Without a new, unbalanced force entering the picture, that status quo remains forever.
We call this stubborn resistance to change inertia. And here is a really fascinating detail. Inertia is directly tied to mass. The heavier an object is, the harder it is to change its mind. If you give a light push to a styrofoam brick, it moves easily, right? But if you give that exact same push to a solid concrete brick, it barely budges. The concrete brick has more mass, which means it has a much, much greater tendency to resist any change to its state of rest.
Let's look at section 3, second law, force and mass.
The absolutely crucial point here is this incredibly elegant equation: force equals mass times acceleration. It's just 3 little letters, but this simple formula forms the entire basis of classical mechanics. It tells us that an object's acceleration depends on just 2 things: the net force acting upon it and the mass of the object itself.
Notice what happens to the math when we tweak our variables. If you push a shopping cart and suddenly double your pushing force, you're going to double the cart's acceleration. But if you load that cart up with heavy groceries so it becomes twice as massive, pushing it with your original force is now going to yield only half the acceleration. So force and acceleration are directly proportional, but mass and acceleration? They're inversely proportional.
Next up, section 4, third law, action meets reaction.
This is perhaps the most famous of Newton's laws. For every action, there is an equal and opposite reaction. It means that every single push or pull in the entire universe comes in a perfectly matched pair. If object A pushes object B pushes right back on object A with the exact same amount of force, just in the complete opposite direction. Now, this brings us to a really fantastic question. If I pull on something and it pulls back on me with the exact same force, why does anything ever move at all? Why don't these equal and opposite forces just mathematically cancel each other out to 0? Well, it is time for some myth busting, because this is the single most common misconception about dynamics.
The secret is that these paired forces don't cancel out because they act on entirely different objects. Let's look at gravity. The Earth exerts a downward gravitational pull on a falling apple. That is the action force. The reaction force is the apple exerting an upward gravitational pull on the Earth. The forces are completely equal in magnitude. However, remember our second law, F equals ma? Because the Earth has a massive amount of inertia compared to the tiny apple, the Earth's acceleration is incredibly close to 0. The apple, on the other hand, is the one that visibly accelerates toward the ground. Finally, Section 5, Dynamics in Daily Life.
Breaking down a rocket launch is just a perfect display of dynamics. A lot of people mistakenly think rockets push off the ground or even the air. Actually, they don't. The rocket engine violently pushes burning exhaust gases downward. That's the action force. According to the third law, those gases simultaneously push the rocket upward. That is the reaction force causing the lift. And as the rocket burns through its heavy fuel, its overall mass decreases. So according to the second law, with a constant thrust and a decreasing mass, the rocket accelerates faster and faster into space.
Bringing it back down to Earth, understanding dynamics literally saves lives in a car crash. If a car hits a wall, an unbalanced force stops that vehicle instantly. But according to the first law, the law of inertia, the passenger inside wants to keep moving forward at the original speed. Without a seatbelt, the passenger would just continue in motion until hitting the windshield. The seatbelt intervenes, applying the necessary unbalanced force to counteract the body's inertia safely.
And this brilliantly illustrates how even something as simple as going for a swim is a total masterclass in dynamics. When you swim, you aren't just magically moving through the water. Your hands are actively applying a force to push the water backward. The equal and opposite reaction, the water pushes your body forward. You are utilizing action-reaction pairs to propel yourself all the way across the pool.
Hopefully, you now have an entirely new lens through which to view the physical world. For example, you aren't just passively sitting down right now. Gravity is pulling you into your chair, and your chair is actively exerting a normal force right back up to keep you from falling. So I'll leave you with this to ponder. As you go about the rest of your day, what other invisible forces are secretly interacting with your body at every single moment?